So hello everyone. So I just wanted to go through quickly go through midterm one, some content with you guys since there seemed to have been an error with the recording for the recitation. So some of the questions I'm going to go more in depth into, and then some I'll leave for you guys to work out. So to begin with, the first question, and don't just go type this into a translator, as that's kind of the easy way out. So I'm gonna give you guys a chance to pause, or pause the video, and then try and translate both of these instructions into hexadecimal. So I'll give you a second to pause, and then I'll go over the solution. Okay, so hopefully now you've worked it out and hopefully you've gotten the following answers. So it's pretty straightforward. So an add-I is an immediate I-type instruction, and this XOR is a R-type register-to-register instruction. So all you have to do is just the standard translations, which we did in class. You get the opcode, you encode the register or registers, you get the funct3, and then you set, in the case of the add-I, you set that 0x00C, which is the 12 in binary, or 12 in hexadecimal. And as an additional question to think about, what does the second instruction, the XOR x3, x3, x3 do? So what it does in this case is it instantly clears the register. So no matter what is in register 3 in this instance, it will get cleared because anything XORed with itself we just evaluate to 0. So this is actually really commonly used in a lot of instances to clear registers. So the next question, I'll give you a second to pause here again, but the following data word is stored in memory, so hexadecimal 1278634. It's stored as shown in the table. So all you have to answer is this big or little endian. So hopefully you've gotten that the answer is big endian. And this is because in big endian, the more significant bits are at lower memory addresses. So so you see 0x12, those are the most significant bits in this instance, and those are at the lowest memory address. So you can see that they're at address 1004, which is the lowest one. Then you go down to address 1005, it's 0x78, which is the second most significant set of bits, and you go all the way down. So if this was little endian instead of big endian, what would end up happening would just be the inverse. So address 0x1004 would hold 0x34, 0x1005 would hold 0x86, and so on. So it would just go the opposite way. So this is a really good question as well for the exam, and it encourages you to think some. And this is kind of a two-part question. So the next slide will also be considering this question. So consider the 7-stage processor below. The designer added a register read, which can handle the reading of the register file, and a route, which routes the data from the register file to the ALU. So you can see the processor here, the 7 stages, and you can see the time taken for each stage. So what would the clock cycle be if this was a single cycle processor? And what should the clock cycle be if it was a pipelined processor? So I'll give you a second to pause and work it all out, or pause the video and work it all out if you'd like, and then I will reveal the answers. Okay, so hopefully you have the answers now. So all you have to do is for a single cycled processor, you need to make sure that the clock or the clock period can encompass all of the stages at once. So you need to go and add them all together. So to find this, you do 200 plus 100 plus 200 plus 150 plus 175 plus 350 plus 200. And then you'd get that the single cycled processor would need to have a clock period of 1,375 picoseconds. So now for a pipeline processor, and this is the big benefit in pipelining, we can increase the amount of clock cycles we have in a given time because we don't need to wait for every stage to complete. It is limited by the slowest stage because we need to wait till that completes till we can move everything forward. So in this instance, you can see that the slowest stage is memory, and generally memory is the slowest stage. But you should always look at everything and make sure. But generally, memory is the longest stage in a processor. In this instance, it's 350 picoseconds. So therefore, the clock period for the pipeline processor should be 350 picoseconds. So now, expanding on this question, what stages could you combine in the 7-stage pipeline version without increasing the clock period? So I'll give you a second to think about this as well, and then maybe pause the video, and then I'll come back with the answer in a moment. Okay, so hopefully you managed to see that there are actually many stages you can combine here. So for example, you just want, since the pipeline processor has a period of 350 picoseconds right now, with the memory stage being the longest one, we need to combine stages such that the combination of their time is less than 350 picoseconds. So in this instance, we can combine fetch and decode, right? That's 200 picoseconds plus 100 picoseconds, which is 300 picoseconds, less than 350. We can combine route and execute. That's less than 350 picoseconds. We can decode, or we can combine decode and reg read. That's also 300 picoseconds, which is less than 350. So there's a lot of stages we can combine here. There's many answers to this question. So what you'd be looking for in this instance is just two conditions. The first condition being that the sum of them, the sum of their times is less than 350 picoseconds. And then additionally that they're back-to-back stages, right? We can't combine decode and memory. That doesn't make sense. We can't combine fetch and memory. We don't know that it's a memory instruction as we're fetching it. And we haven't even done all the execute stuff we'd need to anyways. So we actually had a really good question in the recitation about this. Can I combine more than two stages? And the answer is yes. You can combine multiple stages as long as they're consecutive. So now we'll go into an Amdahl's law question. So in this instance, we have an update to a logic transistor, and this update can speed up 15% of the instructions by a factor of 3.5. So what would be the speed up of the new processor? If the original processor takes 10 seconds to execute a given code segment, how long would it take to execute that same code segment on the new processor? So pause the video here and try and work it out, and I'll come back with the answers in a moment. Okay, so hopefully you have an answer at this point. So the first thing we need to know is Amdahl's law. And in this instance, we're going to take the speed. We need to find f and p, right? So f is the speed up in this instance, which is 15%. So we can frame that as 0.15. And p is the factor of speed up. So f is how much it can speed up. P is how much it can speed it up by. So p would be 3.5 in this instance. F would be 0.15. So just plugging this into our equation, we get 1 over 1 minus 0.15 plus 0.15 over 3.5. So given this should give us a speed up of 1.12. Now, to find the time of the new code, since it's faster, it should be less. So we take the time of the new code, or the time of the old code, which is 10, and multiply it by 1 over the speed up. So 1 over 1.12. In doing this time of the old code times the inverse of the speed up will get us a result of 8.93 seconds. So this question we went over in a previous recitation as well. But it is a very good question because it has a ton of tricks in it. So I'll give you a moment to work this out if you haven't seen the previous recitation. Um, and then I'll get back with the solution. Okay, so hopefully you've written out the table. So in this instance, there's a couple things we want to look for. So the first thing is there a dependency between instruction 1 and instruction 2? So yes, there is a dependency, but not one where we need to stall in this instance, because we store a word into the address of whatever is in register 5, and then we load a word from that same address in the following instruction. But this is fine, right? Because we put the word, we put whatever's in register 4 into the memory location held by register 5 at cycle 4. So all we have to do is load that word again in cycle 5 when instruction 2 gets there. So even though this is technically a dependency, it's not one we need to worry about. So now going from instruction 2 to instruction 3. Now we are trying to get the value at register 1. So we fetch in cycle 3 because there was no stall previously. We decode it in instruction 4, and we can't move forward to the execute stage yet. So we can't forward here. We can't forward from this execute memory latch forward or back to execute because we don't have the value yet, right? It's a load word, so we're getting the value from memory. So we need to wait till cycle 5 is complete so that the value from the address held in register 5 is loaded into register 1. Then we can forward that value from register 1 in the latch between the memory and write back stage back to execute. That's why we only stall one cycle here instead of 2. So we stall one cycle and then we continue like normal. Now we need to look for instruction 4. So this uses register 3, which we just used in instruction 3. So we have to wait here. We need to wait because we can't we need to wait in instruction 5. We need to stay in fetch because we cannot have more than one instruction in the same stage at the same time. So one instruction per stage at all times. So it needs to stay in fetch. So when it goes to decode in cycle 6, we can just forward from the next stage, right? We have the value at the end of the execute stage, or we have the value of register 3 at the end of the execute stage in cycle 6. Therefore, we can forward this value to be used from the execute memory latch back to execute to be used in instruction 4. So we don't need to stall here again. So therefore, we can just go straight into execute in cycle 7 and then proceed with the memory and write backs in cycle 8 and 9 as normal. So now this question also asked you to calculate the CPI. So what we do in this instance is we start at cycle 5. So we take cycles 5, 6, 7, 8, and 9. So 5 cycles and divide that by 4 because we have 4 instruction cycles per instruction, which gives us the CPI of 5 over 4, which is 1.25. Okay, now this is a little bit of a longer question, so again, pause the video and work through it, and then I will go through the solutions as well. Okay, so in this question, we have a BHT table with the state or with the initial states given, and we're told to use bits 5 and 4 from the BHT index, which are, if we look at the hexadecimal version, which is what we're given, then we know that's the least 2 significant bits of the second hexadecimal value from the right. So in this first one, we need to find the least 2 significant bits of 0x4, since it's and this is just 0, 0, right? So we know our index is 0. Since this is actually taken, we need to update the state by adding 1 to our state machine. So it becomes 1, 1. Now we go to our next instruction. Again, it goes to index 0 because bits 5 and 4 are 0, 0. So now it's actually taken, but we can't update our state machine because what happens when we're in the highest state? We only have 2 bits, so 1, 1. So we can't really add 1 because we don't have a way to represent that. So it just stays at 1, 1. Now we go to now we go to a new address, 0x00054. So in this instance, we get 5, which has its 2 least significant bits as 0, 1. So therefore it goes to index 1. It's actually taken. We go to the same thing we did before where it's already 1, 1. So it just stays in that state. So then we go to the next instruction, and this is 0x00664. So its 2 bits would be, or its bits 5 and 4 would be the values 1, 0. So since it's 1, 0, that's 2, and it's actually taken, which means we need to update this. So in state 2, we update it to 0, 1 by adding 1 to that state machine. So as you can tell, this will still predict not taken on the next cycle, no matter what. So it's also important to know that if the most significant bit is 0, it will always predict not taken. If the most significant bit is 1 in this instance, it will predict taken. So now we can go on to the next instruction, which is 0x00CCC, and we're assuming this is actually taken. So C in hexadecimal is 1100. So again, the 4 and 5 bit here goes to index 0 as it's 0, 0. And again, it's actually taken. It's already at 1, 1. So we stay in 1, 1. Now we go to 0x00DDC. And in this instance, we're just adding 1 to C, right? So D in D in binary is 1101. Bits 5 and 4 is therefore 0, 1. So we go to index 1. The state is already 1, 1. It's actually taken, so we just stay in that same state. So now we go to the next one, which is 0x01000. And I mean, it's a 0, so you can tell that this is in index 0. It's actually taken, so again, we already have 1, 1, so we just stay in that state. And lastly, we go to 0x02004. So the 5th and 4th bits in this one are 0, 0 again, which goes to the 0th index. But this branch is actually not taken. So in this instance, we subtract 1 from it. So this will go from 1, 1 to 1, 0. And this will leave us with our final solution as shown. So index 0 will hold 1, 0. Index 1 will hold 1, 1. Index 2 will hold 0, 1. And index 3 will hold 1, 0 in the branch history table.